Good morning, one and all. This is Babitha. In the previous lecture, I have taken the topic on test and testability. Let us go to what are the types of faults present in the digital circuits. So these are the contents that are that we are going to see in the today's lecture. So the like introduction to faults in digital circuits, need for fault analysis, controllability, observability, fault models, stuck at faults, bridging faults. CMOS technology considerations and intermittent faults. So these are the contents that we are going to see today in faults in digital circuits. Introduction. Now let us see the introduction to digital faults. So how do faults occur? Faults occur due to manufacturing defects or aging. So when we consider any digital circuit, and if the circuit fails to if the circuit fails to give an appropriate output, so then we say that the circuit is a faulted circuit. So how does this faults occur? So these faults occur with the due to the manufacturing defects or aging of the circuit. So if the circuit is an old circuit, if the circuit based on the manufacturing age, the circuit may become defective. So they cause deviation from the expected logic behavior. How these faults are, how these circuits are said that they are defective when an expected logic outcome is when the expected logic outcome that it has to occur is not proper, then we say that the circuit is a defective circuit. So testing ensures the reliability of the digital IC is important in and this so for this we in order to see whether the circuit is a defective circuit or a proper circuit, testing ensures that ensures the reliability of the circuit. So this is important in VLSI and embedded systems. So the introduction to digital faults is that, so we are trying to see what where the faults occur. Okay, how the faults occur and what is the what are the types of faults. So this is the introduction to digital circuits. So let us see the example of how the faults occur due to manufacturing defects and aging of the circuit is one of the reason, and how we can say that the circuit is a defective circuit. So if you take an example of any digital circuit, for example on a logic AND gate or an OR gate, for a logic AND gate, the output of for 2 input logic AND gate will be 0 0. The output will be 0. If 0 1, the output is 0. 1 0, the output is 0, and 1 1, the output is 1. So this is the output of output for a 2 input AND gate. This Y is the logic output for the input AND gate. But instead, if at all for 1 1 input the output is 0 instead of 1, we say that the logic is that the logic behavior of the circuit is not proper. That means that the circuit is defective. In this way we find the circuit. In order to say that the in order to ensure the reliability of any circuit, we need a testing process. So that is nothing but the test and testability, and we have in VLSI and embedded system, this is very important to test any circuit and find whether it is proper or not, whether a circuit is working properly or not. So sources of faults: manufacturing defects, proper variations, environmental stress, aging, and wear outs. So what are the sources of faults that occur is based on the manufacturing defect. One thing is manufacturing defect causes faults, while manufacturing, any IC, if we consider, if you are during the manufacturing of an IC, what are the steps involved is, first thing we will try to go with the VLSI design flow, where we will try to involve all the different steps, that is trying to design an IC using RTL logic. After that, from there we'll go to the physical design verification, from where we get the different types of operations, whether whether it is reaching the proper specifications or not. After completion of the proper specification, when it is sent to the manufacturing process, if at all there is any leakage of the current in the circuit or some different different faults, manufacturing defects occur. So this is one of the source of the fault. And during the process variations also, we can we say that during the processing of the IC manufacturing, there may be different faults that occur, and the environmental stress while designing an IC based on the environmental process. Like for example, when you are trying to manufacture any IC, in that we have number of transistors involved. So that transistors are the connection of the transistors is completely based on the machine machine based on machine oriented. But the thing is, due to the silicon and silicon fabrication process, during the fabrication process, based on the environment also, the circuit may become defective and aging and wear out during the manufacturing process, and whatever the wear outs that occur, the sources faults may occur in the circuit. So the importance of faults testing. So how the faults are being tested, what is the importance of testing the faults is, it improves the productivity, it reduces the failures, enhances the manufacturing yield, and supports design for testability. So the thing is, when you are trying to design one IC, when we are trying to design one IC, that is involved with the number of transistors. So that is involved with number of transistors. If we are not going to manufacture one single IC, so it is in a bulk where number of ICs are being designed. And if there are in a bulk of manufacturing process, if half of the ICs manufactured are defective, then the complete process, then the complete manufacturing and the complete process that is done for the that has taken place for manufacturing the complete IC, fabrication of IC, that complete thing will be wasted. So instead of reaching that wastage, we can improve the productivity and the reliability, and which reduces the field failures and enhances the manufacturing field. When the design manufacturing, if at all we have 80 ICs to be manufactured, and all the 80 ICs that are manufactured are completely productive, and there is no defective piece in it, so that enhances the manufacturing yield. So for that reason, we need the design for testability. So that is the importance of faults in testing. And so when we come into so the next slide shows the concept of controllability. So during manufacturing, whatever we have seen, those are the faults, and how those faults are going to be tested. So now in design for testability, it supports design for testability. So the design for testability, we have two different concepts, that is controllability and observability. So the controllability is that it's ability to set internal nodes to logic 0 or logic 1. High controllability simplifies testing, and inputs should influence the nodes easily. So when you are trying to go for a controllability is the ability to set the nodes of zeros and ones logic. So which simplifies the testing. When we are going for a process of for the testing process, its the ability to set the logic to 0 or 1 is nothing but the controllability, and is nothing but controllability, and the inputs should be within the nodes. Within the nodes, that is, if at all we take any circuit, example of an AND gate, if I'm taking a circuit, and the nodes are the input nodes, A, B are my inputs. If these nodes are set to either 0 or 1, so this is the controllability. So that means, in order to get 0 as the output, I need to set these logics to either 0 or 1. That is my controllability. So this is the ability to set these logics, to either 0 or 1 is nothing but the controllability. This setting of logic 0 or 1 will simplify the testing, so that we get the proper output, and that one will be assigned with the internal nodes only. That is, the internal nodes are also nothing but my inputs. So this is what controllability is, the ability to set the internal nodes to either logic 0 or 1. For example, if I take an OR gate also, if I take an example of an OR gate also, what happens is, I will set my input nodes to 0 or 1. If at all I go for any other circuit like XOR gate or any other gate, or else if I take for an answer adder circuit also, if I take, I have 3 inputs A, B, C in. If I keep these logics as 0, 1, 0, these are my inputs, so I may get the output sum and carry. So these are the things that I am trying to set to control this my input logics. So these are given to the nodes of input nodes. So this one is nothing but the controllability. Next comes the observability, ability to observe internal node values at the outputs. The controllability is exactly what is completely under input node, and the observability is with the output node. So whatever the circuit diagram that we have seen for A, B input and gate, so this is nothing but 0, 1, whatever the logics that I am trying to keep over here. The observability is nothing but to observe at the values at the output values helps to detect the internal faults. If at all I get the output as 0 over here, it means that the output that is that we have to get for the AND gate for 0 and 1 combination is 0s, and then the device is not a defective piece. If at all I get the output as 1, then that is said as the faulted one. So the important for this is important for fault propagation, whether so the control of the observability and the controllability will be seen in testing. So in both the properties affect the fault detection efficiency. Design techniques improve testability used in scan design and DFT techniques. So this controllability and observability when testing will prove the detection efficiency, and these are used to improve the design for testability. So and these are used in scan design and DFT techniques. So design for testability is nothing but when we are trying to test any circuit, that one you are giving to circuit under test, that is called as circuit under test. You are trying to give an input to which circuit you are trying to test. Okay, that tested circuit is nothing but you are giving to the circuit under test. The output that you are going to get, that output will be verified with the example of a feedback circuit, will provide some of the specific outputs. If those specific outputs are matched with the output, then again you will get the will get the information whether the circuit is proper or not. So this complete process is nothing but the DFT. In DFT, when you are trying to give an input to a circuit and check the output, that output is again fed as the feedback, and with the specified outputs, checked whether the outputs that we are getting are proper or not, and we'll get the information. That is called as uh, uh, design for testability. So this in design for testability, we have different types of testing process. So the one is nothing but your scan design test. So this is nothing. This is the design for testability process. Fault models. Now the fault models represent the possible defects. Mathematical representation of possible defects simplifies testing analysis. Common faults includes stuck at and bridging faults. So this is all what we have seen are the different types of testing, the concepts of testing in concepts of testing, and what are the types of faults that occur in testing. We have two different types of fault models, that is stuck at fault model and bridging model. In stuck at fault model, we have stuck at 0 and stuck at 1. Let us see what is the example of stuck at 0 and stuck at 1. So stuck at 0 model is nothing but stuck at fault model. Output stuck at 1 fault test vector is A is equal to 0. For the circuit, this is the AND circuit that we are taking, A and B. If A is equal to 0 and B is equal to 0, the output should be Y is equal to 0. Right, the output should be Y is equal to 0. But instead of Y is equal to 0, if I get Y is equal to 1, I say that it is a stuck at 1 fault. This is called as stuck at 1 fault. Okay, because the fault is getting with the output at 1. Instead of 0, I am getting 1. The fault is at 1. So that's why we are saying this is a stuck at 1 fault. If at all I get 0, 1, 1, 1, I will give the input. The next one, if at all I give the input as 1 and 1, I need to get the output as 1. I need to get Y is equal to 1 as my output. But instead of Y is equal to 1, if at all I get the output as 0, I say that it has a stuck at 0 fault. So we have two different types of stuck at 0 and stuck at 1 faults. What is stuck at 0 and stuck at 1? Signal permanently fixed at logic 0 or logic 1 is nothing but your stuck at fault. Stuck at fault will be either at 0 fault or stuck at 1 fault. Stuck at 0 fault is nothing but if at all I have to get my output as 0 but the output is stuck at 1, then I say that it has a stuck at 0 fault. If at all I have to get the output as 1 and I am getting if at all I have to get the output as 0 and I am getting the output as 1, then I say that it has a stuck at 1 fault. So these two are the stuck at faults, stuck at 0 and stuck at 1 faults. So this is the example of stuck at fault. Now how we will detect the faults? How we detect the faults? So already this example has been explained how we detect the faults. Example here itself. See, apply the input test vectors. We apply the input test vectors to any circuit, whatever it may be. Observe the output behavior. Mismatch indicates presence of fault indicates that there is a presence of fault. Example, OR gate I have taken 0, 0. My output must be 0. But if at all I get 1 as the output, then I say that there is a fault. So this behavior is for each and every circuit, whatever the circuit may be, an adder, a multiplier, a multiplexer, a demultiplexer, a controller, whatever the circuit that we are going to take, every circuit will be the same. So these are the inputs that you are giving, those are called as the test vectors. So these are called as the test vectors. So when we are trying to observe the output, if the output that what if there is an at the observation of the output, if there is a mismatch, it indicates that there is the fault in the circuit. So now the next thing is the bridging faults. So the bridging faults occur when two signal lines short together. This may create wired and or wired logic behavior. So for example, here it is given that bridging faults occur when two signal lines short together. Example, if these are short together, then there will be a bridging fault occurs. For example, this is a PMOS circuit, and this is an NMOS circuit. If these are short due to the okay, let me show you the circuit diagram of this PMOS and NMOS. One second. Okay, if these are short due to the high power, if these are short due to the high power, if these PMOS and NMOS are shortened due to the high power, then the output that you are going to get over here, 0 1, if I give 0 1 and I need to get the output as 0, but the output that I am getting is 1 due to the high power that is generated due to the shorted circuit, then this fault is nothing but bridging fault. This is nothing but the bridging fault. So this may create wired and or wired or logic. So when a circuit is going to get shortened over there, what happens is the circuit may become a wired AND circuit or a wired OR circuit. So this is nothing but the CMOS inverter circuit example, PMOS and NMOS. If it is shortened due to the high power, it is nothing but your fault, bridging fault. If the two lines are shortened due to the high power, if the two lines, bridging faults occur when two signals are shortened due to the high power. Okay, this completes the different types of faults in digital circuits, and the next thing is how these faults are being tested using different logics. So in DFT we have different types of testing logics. What are those? Let us see. In DFT we have different types of testing logics, like using ATPG we check, that is automatical test pattern. Using manual we check, and using ATPG we will see automatic test pattern generation. We have built-in self-test. In the next lecture we are going to see what is built-in self-test and what is ATPG. Thank you.